Assalamu alaikum, dear students and friends. Today we will discuss the solution of assignment based on chemical reactions of alkenes. The first question of the assignment was to draw the structure of the products that are formed when pent 1-ene reacts with each of the following reagents. So these 15 reagents were given and that were asked when they are reacted with the pent 1-ene what the product is. So this is the structure of pent 1-ene because with pent 1-ene it means a chain of 5 carbons with a double bond between the first and the second carbon. So now let us discuss these 15 reactions sequentially. The first reaction was asked about the interaction of hydrogen gas in the presence of platinum as a catalyst when treated with the pent 1-ene. So what product do you expect? It's a simple hydrogenation reaction. The two atomic hydrogens are added across the double bond to have this saturated version, which is called the pentane in this particular case. So this is a simple reduction reaction or hydrogenation of alkene to give the alkene. The second reaction was the addition of HBr to the pent 1-ene. As you know that HBr is a polar molecule and HBr is acid as well. So you must be expecting the first step to be the protonation of this double bond with this HBr. When the hydrogen adds across the double bond, we have a carbocation to the other part of the carbon. So now the question is where the hydrogen of HBr will attach, either to this carbon or to this carbon. If the hydrogen of HBr attaches to this carbon, we will have a double carbocation here, which will be called the secondary carbocation. And if the hydrogen of HBr attaches here, we will have the carbocation here. In this case, we will have the primary carbocation. So as we know that secondary carbocations are more stable than the primary carbocation. So the H must attach to this terminal position so that we have the secondary carbocation which will be immediately captured by the nucleophile Br bromide ion. So overall we will have the addition of HBr in which the H will attach here and the Br will attach here. This is in accordance with the Markovnikov rule. For the third reaction, again we have the entry of HBr to the pent 1-ene, but this time we also have this dialkyl peroxide in the presence of sunlight. Here, the reverse of the regio selectivity will occur. Rather than adding the Br here and H here, we will have the reverse phenomena. First, let me show you the product directly. But why this reversal of regiochemistry occurred in this particular case? It's because this mechanism of this third reaction did not go via the polar mechanism. As I discussed for the reaction 2, I mentioned that the double bond will be protonated to have this secondary carbocation, which will be immediately attacked by the bromide anion. But in this particular case, for the first step will not be the attack of this alkene to the H of HBr. Rather, it will be a homolytic cleavage of this dialkyl peroxide into the alkoxy radical in the presence of this sunlight. And then this alkoxy radical will abstract this hydrogen radical from HBr to leave this bromine radical. Then this bromine radical will attack this terminal carbon to have this CBr bond and a radical here to this position, which is called the secondary radical. And then this secondary radical will abstract the proton from the alcohol, which was just formed in the last step, to have the overall product. Basically, we were not asked to draw the mechanism of these reactions. So that is why I have not shown you the mechanism, but I just simply explained what the mechanism would be so that we may predict the product easily. If you are not getting, you have to just accept the fact that when HBr is added to the alkene, it simply follows the Markovnikov rule. But when HBr in the presence of dialkyl peroxide and sunlight is added to the alkene, it follows the anti-Markovnikov rule. Now let us discuss the fourth reaction. Here in this particular case, we have the addition of H2O across the double bond in the catalytic amount of sulfuric acid present. So it's a simple hydration reaction, and as discussed for the HBr addition to the alkene, it simply goes in the same pattern that first of all this alkene will be protonated in the presence of this acid to have the secondary carbocation, which will be immediately attacked by the water molecule. Later, upon deprotonation, will afford the secondary alcohol as the product. And again, this reaction is in accordance of the Markovnikov rule, which we have discussed in the video whose link I have shared. Now, this reaction is again an example of hydration of alkene, and it will also give the same pattern of hydration, that is the Markovnikov pattern. This is called the mercuric acetate, THF, tetrahydrofuran, and water. These are the solvents for this reaction. And then in the second step, we will have the sodium borohydride's entry to remove the mercury, which the second step is called the demercuration, and first step is called the mercuration, and we have the same alcohol. Now, here you may ask a question: if we have the same product, that is the secondary alcohol, in the fourth reaction and in the fifth reaction, then what is the utility of these expensive reagents to have the secondary alcohol, which we could have got with water and sulfuric acid easily? Well, in this particular example, there is no difference. And yes, if you need the secondary alcohol, it is uh, stupidity to use this mercuric acetate and THF water and later sodium borohydride. Rather, we could have used this simply cheap reagents. But uh, we use this oxymercuration demercuration reaction when we want to avoid the rearrangement of alkyls. However, in case of the hydration of alcohol in the presence of acid, the rearrangement also occurs whenever there is a possibility. In this particular case, we do not have any possibility of the rearrangement. So here, both reagents will give us the same product, that is the secondary alcohol. Now let us discuss the sixth reaction of alkene, that is the pent-1-ene plus borohydride tetrahydrofuran, and then sodium, then hydrogen peroxide and sodium hydroxide. So when we use the term then, it means it is the second step. So whatever is written before the word then is the first step, and whatever is written after the word then, it is the second step. So this is an example of hydration reaction of alkene. Again, now this is the third way to hydrate the alkene. The first two ways we have shown you. In the fourth reaction and in the fifth reaction, both gave the Markovnikov product, that is the hydroxy added to the carbon which has the lesser number of hydrogens. But here the reverse will occur, and we will have this hydroxy attached to the terminal of carbon, that is to the carbon that has a higher number of hydrogens. So this is the anti-Markovnikov selectivity. And why this reversal of regio selectivity occurred, the answer of this question is hidden in the mechanism, which we were not asked. So I will not show you the mechanism, but let me tell you some wordings about the mechanism. The first step will be the attack of this alkene pi bond to the empty orbital of this boron of borohydride, which will simply give you the intermediate alkyl borane, and later uh, the attack of another molecule of alkene to that alkyl borane will give you the borohydride, the B negative anion, and upon uh, sorry, the we will have this alkyl borane here, and then this sodium hydroxide will abstract this this hydrogen peroxide hydrogen to have the hydroperoxide anion, which will attack this alkyl borane. And after so many steps, at the very end, we will have this anti-Markovnikov product in our hand. So the mechanism is not asked, so that is why I'm not showing you the mechanism. And without mechanism, you cannot grip the wording that I'm trying to communicate. So just accept the fact that in the presence of borane, we have the hydroxy attached to the to the hydrogen which has the higher to the carbon which has the higher number of hydrogens. Now let us discuss the seventh reaction of the pent-1-ene with the osmium tetroxide and then sodium bisulfide in water. It is simply an example of dihydroxylation. So we will have the two hydroxys attached across the double bonds, and they both came from the same side. So the delivery is syn in nature. For the eighth reaction, it is the reaction of pent-1-ene with the bromine in carbon tetrachloride with bromine Br2. We have the two bromines attached to the terminals of the carbon-carbon double bonds. It's simply called the dibromination step. And here the role of CCl4 is nothing but just a solvent, because CCl4 is inert for this particular system. However, if we simply replace the carbon tetrachloride solvent with a water, so what will happen? This time we will not end up with the dibrominated alkane. Rather, we will have one bromine replaced with the hydroxy in the product. So this is called the bromohydrine, which because we have the bromo and the hydrine as well. So we have formed the bromohydrine molecule. How did it occur? Again, this thing is hidden in the mechanism. The first step of the alkene with the bromine is the three-membered bromine containing ring, which is called the bromonium ion. And then in the reaction 8, nothing was present to attack that bromonium ion except the remaining bromide anion. So the Br negative anion opened that bromonium ion to have the entry of the second bromine. But in the ninth reaction, we have the water as a nucleophile present in competition with the bromide anion to open the bromonium ion, and then the water will open this bromonium and bromonium ion ring to have the bromohydrine formation. And in the 10th reaction, we have again the pent-1-ene and bromine, but this time the solvent is not the water, but it's methanol. So you must be expecting that this time the OH will be replaced with the OMe, with the methoxy group. And yes, we have the replacement of OH with the methoxy group. Again, the mechanism tells the complete story. First of all, this alkene will react with this Br2 molecule to have the three-membered bromine containing ring, which is called the bromonium ion. And this time we have the methanol present as a nucleophile, which will open this bromonium ring, and we have the entry of OMe in the molecule. Now let us discuss the 11th reaction. The pent-1-ene reacted with the ozone O3 and followed by the reaction with the dimethyl sulfide. So it's a two-step reaction. And yes, with ozone, we have the breakage of carbon-carbon double bond. So this carbon-carbon double bond will be broken, and once it is broken, we will end up with the 4 carbon molecule because of 1, 2, 3, and 4 carbons and 1 carbon molecule. So we will have 2 molecules. One is 4 carbon molecule, the other is 1 carbon molecule. And when both carbons are broken, we have the oxygen attached to the both carbon, which will give us the 2 carbonyls, and with dimethyl sulfide basically dimethyl sulfide is used to break the intermediate which was formed during the reaction, and the reaction ended with the aldehydes, because we have the hydrogen here and the hydrogens here. However, when we use the sodium borohydride in replacement with the dimethyl sulfide, we will have not the same product. Obviously, we will have the reduced versions of the product. That is, for the formaldehyde, we will have this methyl alcohol, because when we reduce the formaldehyde with sodium borohydride, we will have the methyl alcohol. And for the butanol, we have the butanol, the butane 1-ol as the product. So the only difference between the 11th and the 10th and 12th reaction is the reduction of the product that was formed. And again, if you have gripped the concept what the sodium borohydride did, so this time rather than reducing, we have the oxidizing agent that is called the hydrogen peroxide. So we will not have this methyl alcohol or the butanol, rather we will have this methanoic acid and the butanoic acid. So these are the reduced versions, and these are the oxidized versions of these reagents. So basically all these three reactions are called the ozonolysis, and the second step differs. So the complete name of the first of this 11th reaction is ozonolysis followed by the neutral workup, and for the 12th reaction we call it ozonolysis followed by the reductive workup, and for the 13th reaction we call it ozonolysis followed by the oxidative workup. For the 14th reaction, we have the entry of metachloroperbenzoic acid MCPBA in the presence of dichloromethane. Dichloromethane is simply a non-reacting solvent. So we have the epoxide formed across the double bond. This oxygen of this epoxide or the oxylane ring, it must have come from the oxygen which is present in this metachloroperbenzoic acid. You may find the chemical structure of metachloroperbenzoic acid to know how many oxygens are there. In fact, there are 3 oxygens in metachloroperbenzoic acid, but the oxygen which is attached with the hydrogen at the very end is the oxygen that is given to this double bonded carbon to have this 3-membered oxygen containing ring, which is called the epoxide or the oxylane ring. For the last reaction of the question 1, it says when pent 1-ene reacts with diiodomethane in the presence of zinc copper, we have a simply cyclopropionation occurred for this reactant. So if you compare the 14th and the 15th reaction, the difference is the oxygen and the CH2. Here the oxygen came from the MCPB as discussed, and here this CH2 that is called the methylene, it has come from this diiodomethane. Now let us discuss the question number 2. It says starting with 2-methyl-but-1-ene and using any other needed reagents, show how each of the following could be synthesized. So basically it has 5 parts, and this is the structure of 2-methyl-but-1-ene. You could see we have a chain of 4 carbons, 1, 2, 3, 4, with methyl at position 2 and the ene at position 1, that is a double bond at position 1. So this is the starting material, and from this 2-methyl-but-1-ene we have to make the compound 1, 2, 3, 4 and 5. So this is the first compound which is to be formed from this starting material. So what reagents do you expect to be used to have this compound 1? Simply you could see the bromine has been added to the double bond, and obviously the hydrogen has also been added to the double bond. So we have the HBr as a reagent that must have been used with the 2-methyl-but-1-ene to afford 1. But wait, if we use the HBr, we will not get the compound 1. Rather, we will get the bromine here and the hydrogen here, the reverse of this compound one. Because we know the Markovnikov rule says we have the addition of hydrogen to that part of the carbon-carbon double bond which has the higher number of hydrogen. So hydrogen will add here and the bromine will add here. So this is the reversal of what we are expecting. So we have to use the HBr, but this time we will also have to use the dialkyl peroxide and in the presence of sunlight, which is called the anti-Markovnikov addition of HBr. For the compound 2, we simply have a ketone, and also you could, if you could count the number of carbons, we have 4 carbons here and we were having the total 5 carbons here. So one carbon also has been lost. So what could be the the reagents to convert into two? The starting material into compound 2 is the ozonolysis. Because we discussed in the question number 1, when the carbon-carbon double bond is broken, we have the 2 carbonyls, and then upon neutral workup, we may have the aldehyde or ketone. So here the formaldehyde must also have been formed, which is not shown. And this is a very easy reaction because we have simply the oxygen, appearance of oxygen across the carbon-carbon double bond in a 3-membered ring, which must have come from and treating this 2-methyl-1-ene with the metachloroperbenzoic acid in the presence in the DCM as a solvent. This is the oxidation reaction of the alkene. Here again, it is very easy reaction because we have simply the hydration of this carbon-carbon double bond. And yes, it is an acid catalyzed reaction because when the hydrogen of the acid attached to the terminal carbon of this carbon-carbon double bond, we have this tertiary carbocation center, which will be immediately captured by the water molecule. And later upon deprotonation, we will have the compound 4. For the last reaction, you may simply expect what the reagents must be used to have the compound 5. You expected right. We have simply addition of hydrogen molecule in the presence of platinum catalyst. That is the hydrogenation of this alkene to afford the corresponding alkene. So these are the questions that were asked in the assignment, and these are the solution of the questions. Thank you very much.